So the last talk in section 1 is a joint of Vasyl Petrychkovych and Natalia Dzhaliuk of Pidstryhach Institute for Applied Problem of Mechanics and Mathematics of the NACS of Ukraine. Its title is the Sylvester matrix polynomial equation and its solution. So we see the presentation. Yes, Natalia.
And good afternoon. My name is Natalia Dzhaliuk.
Good afternoon.
And I present the report together with Professor Vasyl Petrychkovych. Firstly, we thank the organizer of this conference for opportunity to present our report, because in this very hard time for our country, that Ukrainians are fighting against the brutal invasion of Russia, they organized this conference at very high level. The Sylvester type matrix equation are called the matrix linear bilateral equations of 1 and 2 variables, 1 and 2, where A, B, and C are matrices of appropriate size over a certain field F or over a ring R. X, Y are unknown matrices of suitable size. The special case is Lyapunov equations, where A, T is a transpose of matrix A, and the Diophant matrix equation is in form 3. Matrix equations of different types appear in various branches of mathematics, physics, mechanics, etc. Linear matrix equation, in particular Sylvester type matrix equation and Diophant equations, including matrix polynomial equations, apply in solving problems of the stability theory, the dynamical system theory, and the control theory, and other problems. Solubility conditions of linear matrix equation 1 and 2 over a field and over a ring of polynomials was examined by Rod. Theorem by Rod is the matrix equation 1, where matrices A, B, and C with elements in a field or in a ring of polynomials f of lambda has a solution X with elements in F or F of lambda respectively, if and only if the matrices M and N are similar. The matrix equation 2 has solution X, Y with elements in F or in F of lambda, if and only if the matrices M of and N are equivalent. Many authors extended this theorem on the principal ideal rings, Feinberg, and arbitrary commutative rings, Gustafsson other rings, and for other matrix equations and system of matrix equations. Consider the Sylvester matrix polynomial equations for if the matrix polynomial equations 4 is solvable, it has solutions of unbounded above degrees. So there arises the following natural questions. What is minimal degree of solution of this matrix polynomial equations? This problem was solved only in particular cases. Barnett obtained the following result. The determinants of two regular polynomial matrices A and B of order L R and degrees N M respectively are relatively prime, that is, have greatest common divisor independent of lambda if and only if the equations for a given L times R matrix C with elements of F has a unique solution XY with degree of matrix X less than degree of matrix B and degree of matrix Y less than degree of matrix A. Barnett made the following remarks. The theorem still holds if degree of matrix C less than or equal degree of matrix A plus degree of matrix B minus 2. From Barnett's theorem, we have the condition of existence and uniqueness of bounded degree solutions of the matrix polynomial equation formulated in this corollary. The Sylvester matrix polynomial equations for where A and B are regular polynomial matrices and degree of matrix C less than or equal degree of matrix A plus degree of matrix B minus 2 has unique solution XY such that degree of X less than degree of B, degree of Y Z less than degree of A if and only if the determinants greatest common divisor of this determinants equal 1. That is relatively prime. Feinstein and Barnes such bounded degrees solution of the matrix polynomial equation called minimal and generalized Barnett's theorem when at least one, but not necessarily both, of matrices A or B is regular. Consider the Sylvester matrix polynomial equations for where matrix A and B are monic regular polynomial matrices, that is, their higher coefficients A0 and B0 equal IN, IM respectively, that is, identity matrices. Applies the concept companion matrices of matrix polynomials WA and WB. This equation 4. In this way, it can be reduced this equation to the matrix equations 5 stroke over a field F with one variable z. Professor Petrychkovych used this approach and obtained the uniquest conditions for a solution of bounded degree to one component. Theorem by Petrychkovych, the equation 4 stroke has a unique solution xy degree of X less than degree of B if and only if the determinants are relatively prime. Professor Petrychkovych proposed the method for constructing a solution of matrix polynomial equations 4 stroke. It consists in reducing these matrix polynomial equations to matrix equations 5 over a field F. Methods for solving this equation are well known. If Z is solution of equation 5 stroke, then solution of equation 4 stroke can be written according to the following formulas. We establish the following condition of existence of bounded degree solution in a general case, that is, without restriction of the degree of matrix C. Theorem 1 let the Sylvester matrix polynomial equations for be solvable and be regular matrix, then this equation has solution x, y, such that degree of x less than degree of b, and degree of y less than degree of a, if degree of c less than degree of a plus degree of b, or degree of y equal degree of c minus degree of b, if degree of c greater than or equal degree of a plus degree of b. A similar result is also true when the matrix A of lambda is regular. The next result is theorem 2. Let the Sylvester matrix polynomial equation for be solvable and at least one of the matrices A or B be regular matrix. Then this equation has solution x, y, such that degree of x less than degree of B and degree of y less than degree of A, if and only if degree of C less than degree of A plus degree of B. Next, we investigate the solutions of the matrix polynomial equations for where both matrix coefficients A and B are non-regular matrices. We describe the row and column structure of solution of this equation by using standard form of the collections of polynomial matrices with respect to semi-scalar equivalence. We established the bonds for degrees of solutions of this matrix polynomial equation with respect to degrees of corresponding invariant factors of matrices A and B. A criterion for uniqueness of such solution is pointed out also. These results published in our papers. Recall the definition that we need. Collections of polynomial matrices A1, K, and B1, BK are called semi-scalar equivalent if they exist as scalar matrix U, an invertible matrix VI, such that BI of lambda equal U, AI of lambda, VI of lambda. I equal from 1 to k. This concept was introduced by Professor Kazimierski and Professor Petrychkovych for polynomial matrices over an algebraic closed field on characteristic 0 in this work, and generalized for matrices over an arbitrary field in the work by Petrychkovych. Much later, a similar result was obtained by Diaz da Silva and Lafay. Let pairs of non-singular polynomial matrices A and B from matrix polynomial equations 4 is a semi-scalar equivalent to the pair of triangular matrices TA, TB in a standard form. That is, there exists an upper unitriangular matrix U, an invertible matrix VA and VB, such that TA equal U A of lambda V of lambda, and TB equal U B of lambda V B of lambda, where U I A of lambda are invariant factors of matrix A of lambda. The matrix polynomial equations 4 can be reduced to the associated matrix polynomial equation with triangular coefficients TR and TB in the form 5, where X tilde, Y tilde, and C tilde can be written in the form. we proved the next result for associated matrix polynomial equations 5. Let the matrix polynomial equation 5 be solvable, then it has solutions x1 tilde, y1 tilde, such that degree of row I x1 tilde less than degree of invariant factors mu IA of matrix A minus degree of greatest common divisor of invariant factors mu IA and mu 1b. And solution x2 tilde, y2 tilde, such that degree of column G of matrix x2 tilde less than degree of invariant factors mu JB minus degree of greatest common divisor mu 1a mu JB. And theorem 4 for the matrix equation, given matrix equations 4. Let the matrix polynomial equations 4 be solvable, then it has the following solution. X1, Y1, such that degree Y1 less than degree of Smith normal forms of matrix A minus degree of greatest common divisor of Smith normal forms matrix A and B. And solution x2 y2 such that degree of x2 less than degree of Smith normal forms matrix B minus degree of greatest common divisor of Smith normal forms as A as B. The next corollary describe the column structure, the row structure of the second component of solution. Let SA be the Smith normal form of matrix A. This Smith normal forms has following structure, and then a second component y tilde of solution x tilde y tilde of the associated equation 5 has the following structure. Y tilde of lambda equal y tilde p of lambda is a zero matrix. Y tilde q of lambda is a scalar matrix, and degree of row I y tilde n minus p plus q less than degree mu IA invariant factors matrix A minus degree of greatest common divisor invariant factors mu IA mu 1b. Similarly, we can describe the column structure of the first component of solution. First component x tilde of lambda of solution x tilde y tilde of the associated equation 5. This component has the following structure. X tilde of lambda equal block matrices where x tilde s of lambda equals zero matrix, x tilde t of lambda is scalar matrix, and degree of column G x tilde n minus s plus t of lambda less than degree of invariant factors mu b, minus degree of invariant factors mu 1a, mu JB, their greatest common divisor of these invariant factors. We also established criterion for uniqueness of such solutions for associated matrix polynomial equation 5 in the next theorem 5. A solution of the matrix polynomial equation 5 x1 tilde y1 tilde such that degree of row I y1 tilde less than degree mu ai of lambda and solution x2 tilde y2 tilde such that degree of column J of matrix x2 tilde less than degree of mu JB invariant factors of matrix B. This solution is unique if and only if mu n of A of matrix A and mu n of matrix B, their greatest common divisor equal 1, that is, they is relatively prime, where mu n A and mu n B are invariant factors of matrices A and B respectively. And we proved the next corollary, that is the condition of the existence of bond degree solution to one component for given matrix polynomial equations 4. The matrix polynomial equations 4, where determinants of matrices A and B are relatively prime, has solution x1 y1 such that degree of y1 less than degree of Smith normal form of matrix A, and solution x2 y2 such that degree x2 less than degree of Smith normal form matrix B. And next result, theorem 6, is the generalization of the result of Barnett and Feinstein-Barnett for associated matrix polynomial equation 5, where matrices A of lambda and B of lambda are non-singular only. That is, it is not required that both or at least one of matrices A of lambda and B of lambda be regular. If determinants of matrices A and B are relatively prime and degree C ij tilde of lambda less than degree mu I of lambda plus degree mu n of lambda of B, then associated matrix polynomial equation 5 has the solution x tilde y tilde such that degree of column G of matrix X tilde less than degree of matrix B, and degree of matrix degree of row I of y tilde of lambda less than degree of mu IA of lambda, and this solution is unique. We proposed also the method for construction of solution of matrix polynomial equation 4. It consists in reducing this matrix polynomial equation to the associated matrix polynomial equation 5 with triangular coefficients TA, TB in standard form with respect to semiscalar equivalence. From matrix equation 5, we obtain the system of linear polynomial equation 6. We solve it and make the solution of matrix polynomial equations 5. And by formula 7, we get the solution of the matrix polynomial equations 4. That's all. Thank you for your attention.